Hello and welcome to week 12 of the course on model predictive control. We started off this week recapping some of the things that we have done in the part 2 of this course, starting from week 7 until week 11. Then we picked up one quite important aspect of implementation of MPC, and that is how to do disturbance modeling in order to cover a wide range of cases of both practical as well as theoretical interest. Thereafter, in the past couple of lectures, we took up some classical examples of implementing model predictive control for nonlinear systems with measurement delay, and inferential control. Okay. What I'm going to do today is take up a few interesting papers and discuss about some of the things that have been done in the literature, and these are some of the classical papers in the MPC literature. Okay. So this was a part of a Gyan course that I had given along with Professor J.H. Lee of Korea Advanced Institute of Science and Technology, South Korea. Okay, so this is an acknowledgement to Professor Lee for sharing his material with me, and both of us had conducted this particular lecture in the Gyan course. Okay. Again, this is something that we have talked about multiple times. The exemplary MPC algorithm is we have a plant which takes certain inputs and disturbances and gives out certain outputs. Outputs are the ones that are, some of them are measured, some are unmeasured, and a partial or the complete list of measured plus unmeasured outputs might be controlled. Okay, the entire state is not measured, so we take the output information and we use the model within an observer framework in order to get the state x hat and the information. For example, in case of Kalman filter, the full information is the covariance of the error matrix P infinity or P bar infinity. This is fed to an MPC controller. MPC controller has an objective which is minimization of the deviation from the set point, subject to a linear model or maybe even a non-linear model, and subject to constraints. Okay, that's the key concept behind an MPC algorithm. Okay, so let's look at the overall model structure, and this is a generic model structure. This will encompass both state as well as output disturbance models, and it is quite a bit general in that sense. And the model would be in terms written over here. You may actually have BE multiplied by WK also present over here, and in general there might be a DE term also incorporated over there. And again, the model structure that I have given without the red text is also a fairly generic structure. Okay, and then we had talked about building an MPC controller and so on. Fairly general structure recap from here. No, I won't be presenting this slide. Okay, so now let us take example from this particular work, which was published in 1994 by Yu et al., and that talks about the importance of disturbance modeling in MPC, and there is a comparison between load disturbance or output disturbance model and state disturbance model. Okay, and this controller, MPC controller, was implemented on what is known as a shell oil fractionator problem. So this was a problem that was given by some researchers in Shell Oil Company, and it has industrial relevance. And the problem that they had formulated was, there is something called a fractionator, and a fractionator consists of multiple input streams, multiple output streams, and you have bottom draw, side draw, top draw, and so on. So the bottom draw might be heavy oils, the side draw might be lighter oils, the topmost draw might be some kind of a gaseous material such as LPG, for example, and so on. So it is a MIMO system, it's a non-square system. There are two disturbances 3 inputs and 7 outputs in this example. Okay, and all the transfer function for between inputs and outputs and between disturbances and outputs were given in the Shell Oil Fractionator challenge problem itself, as well as the determination of model plant mismatch was also presented over there. Okay. So, as I had mentioned, there are 7 outputs. Y1 and Y2 are the control variables. They need to be kept at the set point. Y7 is what is known as auxiliary variable, because there is no set point for Y7, but Y7 has to be maintained above a particular minimum value. D1 and D2 are disturbances, and U1, U2, U3 are the manipulated variables. Okay, so as I said, the set point tracking of Y1 and Y2 to minimize U3 as well. Sorry, I forgot to mention about that. And then constraints on MVs as well as the MV rates, basically manipulated variables, as well as input rates, and constraints on 3 outputs, Y1, Y2 and Y7. So this is the overall control problem, and these are the control constraints. The sampling time is given, and as you can see, this is quite characteristic of industrial system. The sampling time is not in terms of hertz or seconds or milliseconds or microseconds or whatever. The sampling time is as large as 1 minute. This is a very huge fractionator, probably 10-story tall or something like that, perhaps. Okay, so it has a very long time response, and there's a lot of dead time and so on, which makes classical control not very easy to implement. Okay, and yeah, so this is the input and disturbance models that have been given. Okay, so the various cases that the authors considered is the load disturbance model case. So as you can see, W1, W2, W3 are the load disturbances that are directly affecting Y1, Y2 and Y7. Now immediately you would notice that because these are additive noise that affect Y1, Y2 and Y7, therefore the controllability condition with respect to integrating white noise and the outputs is already met. The second thing is, because these outputs are also measured outputs, W1, W2, W3 will also be observable from these measured outputs. Okay, so this was one of the criteria that we had discussed in the previous 3 lectures earlier in order to get offset free control. Okay, at the same time, what is happening is we are using these as output disturbances, which means that their response have to wait until all the effects are felt in the output. So the response is probably going to be sluggish, is what we can expect. Okay, and the authors in this paper have used a rate-based formulation. Okay, and this is the results, and what they have shown is without model errors. That means perfect information, the system is able to track the set point very easily. But even in case of model plant mismatch, it is still able to track or ensure offset free tracking, and this is immediately based out of the 2 criteria. What is required for offset free tracking is that the x hat, that is estimated states, and w hat or xw hat, the estimated disturbance state, should tend to xk and x hat k. So what we mean by that, sorry, I should write it down. X hat k given k should tend to xk as k increases, and xw hat k given k should tend to xwk as k increases. Okay, or at the very least asymptotically. If these 2 are guaranteed, then you have estimation which is bias free. Okay, once that is done, we also need to, so this is bias free estimation. This then gets fed into controller, and for controller, c multiplied by x hat k given k should tend to r set point, okay, as k increases. Okay, and both these conditions together guarantee offset free control. Okay, so then the other question was, can you use secondary measurements in order to handle this situation? And if Yes, you can use the secondary measurements also, and it does improve the overall performance. Okay, but what they did over here was that in this particular case, because we had the disturbances that were known, okay, therefore as you can see, the overall performance was much faster than it was as seen earlier. Unfortunately, these disturbances were not estimated from y1, y2, y7, y3 and y5 measurements, okay, because of the observability requirement was not met. Because the observability requirement was not met, using these disturbances as integrating white noise, although resulted in a much faster response, you were not able to guarantee offset-free tracking. Okay, so that was the other result that these authors showed. Okay, so how can you improve this? This, for example, you can have best of both worlds in this particular case by adding the integrated white noise to the outputs, and you have D1 and D2 also being added as integrating white noise. Now, why is this possible? Because only if there are 5 measurements. So there were secondary measurements also. Because there were 5 measurements, you could estimate W1, W2, W3, D1 and D2, and because all 5 of them were estimated, we expect this to get both a fast response as well as offset-free tracking of set points. So fast and offset-free response. I would like to go back a couple of slides. One mistake that I had made over here. What I had mentioned, if I'm not mistaken, what I have mentioned is D1 and D2 are not observable from the measurements. That was incorrect. D1 and D2 indeed are observable from the measurements. If the D1 and D2 are modeled as integrating white noise, we will be able to estimate the disturbance states from the measurement. Why will we be able to estimate? Because we have the GD models that are stable models. So there is a way that D1 and D2 will get estimated. The problem is we have only 2 disturbances but 3 control variables. Okay, so 2 integrating white noise type disturbances will not guarantee the controllability requirements for y1, y2 and y7. Remember what is also needed in order to ensure offset free tracking? It is also required that your integrating white noise you get controllability of your output values based on the integrating white noise. That is something that we had talked about 3 lectures earlier. So the minimum number of integrating white noise required to ensure offset free tracking were 3. Just because you meet minimum number doesn't mean that you will be able to ensure offset free tracking. But if you do not have the minimum number, you will not be able to do offset free tracking. That much is guaranteed. So we needed at least 3 integrating white noise sequences which will ensure that y1, y2 and y7 together are observable. Okay, and because that condition was not met, therefore we could not get offset free tracking in the case number 2. And I have already spoken about case number 3. Okay, so that was the main aspect of that particular paper, which discussed how to guarantee offset free tracking and compared 3 cases. One is state disturbance, one is output disturbance, which ensured offset free tracking but sluggish response. One was state disturbance, but state disturbance was done naively, incorrectly, and as a result you got very fast response but not offset free tracking. There was a steady state bias in the controller. And the third case was when we did both, or when the authors did both, they were able to get offset free tracking and a fast response as well. Okay. Next, I'm quickly going to talk about inferential control paper, and this is paper from IIT Bombay and UC Santa Barbara's group, and this is from 2006, and it's on inferential control. Okay, now this is what is known as a pulp digester. What happens in pulp digester is all the wood chips are sent into the digester along with a digesting material. Usually it's going to contain highly alkaline NaOH solution at very high temperature, and the alkali breaks down all the lignocellulosic biomass, and from the chips you eventually get the paper pulp. The paper pulp is then goes through multiple steps of processing in order to get paper, whether it is cardboard paper or it is writing paper, doesn't matter. The first step is to convert the wood chips into pulp. That is done in a pulp digester that is shown over here. There is a variable called kappa number, which is a quality variable. The kappa number is not measured, but it is estimated from other measurements, that is temperature measurements, alkalinity measurements, and so on. From those measurements you infer what the kappa number value is. Okay, so they had a non-linear process model that they then linearized and used sequentially linear control, if I'm not mistaken, and then they had the disturbance modeling. Okay, what they did over here is that they assumed the decay to be a state noise. Specifically, in fact, they assumed decay to be the input noise, integrating input noise sequence, something that I had spoken about as the three options. The second of the three options was the input noise sequence, and that's what they have implemented. And again, they use the model augmentation exactly in the way that we have studied, in our lectures. And there are various options of model augmentation, and this is from a 2003 paper, if I'm not mistaken. Right, and so they talk about various ways of model augmentation, output augmentation, output disturbance model, input disturbance model, state disturbance model, and a combination of this. This is from Muskie and Rawlings, perhaps. Okay, and they have used the case of a input disturbance model. Input disturbance model is very much like a state disturbance model, with the difference that the disturbance variable or the disturbance matrix is same as the input matrix. Okay, and that's what they have done, and overall model they have ensured that it satisfies the observability criteria. And if again so this is where I said that low disturbances in input is what the authors have considered and ensured that it satisfies the observability criteria. And when they used this for control without any inferential measurements, you see that the kappa number behaves so poorly. Whereas when they do introduce the input disturbance model, the kappa number, they are able to control it at its set point. Okay, so important takeaway from this is, especially when you have inferential control, always, but especially when you have inferential control, appropriate disturbance model becomes extremely important. And again, the concepts that we have studied in this particular week, beginning of this week, are exactly the concepts that were used in this paper as well. Okay, and yeah, this is another result. Okay, now so I've talked about offset-free MPC. I've talked about inferential control. Now let me talk about non-linear MPC, or specifically a variant of non-linear MPC called sequentially linear. Okay, and the estimated equivalent is known as the extended Kalman filter, and this is from a 1994 paper. Okay, so why linearize? So why not use a non-linear MPC? Non-linear optimization is usually very complex to solve. So therefore, what you do is that at each time you first linearize the model, obtain the linearized model, and then implement the MPC. So the question is, how do we use the idea of sequential linearization? At each time you linearize the model, which basically, as I had said a few lectures earlier, for example, AK is computed at xk, uk, dk. As a matter of fact, we should make it a little bit more specific. It's not just at xk, it is at x hat k given k, comma uk minus 1, I'm sorry, this is what it should be, and d hat k given k. Why k minus 1 is because right now at time k we still need to determine uk, so therefore it cannot be linearized at uk. Okay, so once you get A, B and C matrices, you use them in order to get x hat, and with that x hat you predict the trajectory using A, B and C matrices, and the concepts of linear MPC are then applied in the similar manner. So it is linear MPC, but at each time the linear MPC is recomputed using the new matrices AK, BK and CK. That is what this paper talks about. And again, all of this is not for your exam, all of this is not even there for your assignment. I thought it would be a good idea based on the several questions that came up during my class in IITM, as well as several questions that came up during the online sessions. I thought this will be a very good example to take. And when I was working in industry, we use what is known as the moving horizon estimator, as well as extended Kalman filter in estimation, and sequential linear MPC as well as linear MPC is what we use for control. Okay, so it is these types of examples are also today industrially quite relevant. Okay, and again, you basically you have this is the system model, the one-step prediction equation, the prediction error is this, and the covariance is this, and this is the one step ahead covariance. From the one step ahead covariance, you use the Kalman filter Riccati equations in order to calculate the Kalman filter, and then to calculate P, and then you can go back and use calculate P bar k plus 1 at k as the next step. So it all goes on recursively all the time, and this is the measurement correction that can be implemented. Okay, so the important thing is ABC matrices are not constant, so everything remains the same except that instead of ABC you are replacing them by AK, BK and CK, and I have color coded it so that it is easy for you to see. And again, if you are interested in this work either for your current work in industry or in your research, please don't rely on my notes. You should look at the 1994 paper from Rawlings and Lee. Okay, and yeah, I have already spoken about the extended Kalman filter. Okay, MPC uses the same concepts. There's a process model, there's a disturbance model, and the one-step prediction. Okay, for the one-step prediction, they do use the original nonlinear model, but the future predictions they use a linear model. So the original nonlinear model, assuming that u is kept constant at uk minus 1, and the difference between what uk minus 1 gives versus uk minus I, or sorry, uk plus I gives, that difference is captured by this particular term. Okay, so this is for 2 steps, then multi-step, and so on and so forth, and you can build a model of this nature. So this is kind of the non-linear component, I think. No, this is not the non-linear component. This is the non-linear component. Okay, so in linear model, this is Sx multiplied by x hat k given k. This is replaced by a non-linear term like this. This is nothing but our IP multiplied by EK equivalent, I think, right? This one is nothing but SD multiplied by DK term, okay? And this is SU multiplied by delta UM. Okay, so these are the various terms. Okay, so the idea is that this is uk minus 1, and we linearize the system around uk minus 1, and this is the prediction on the linearized trajectory. Okay, based on that we get our AK matrix, BK matrix and CK matrix, and using AK, BK and CK we try out various possible sets of inputs and optimize on the best possible input. Okay, and this is the optimal trajectory that we might have obtained, but we don't implement all the future moves. We only implement the move at time k. Okay, and it goes on into the future, and again rest of it is the implementation. This is the prediction equation over here. This is the objective function, and these are the various constraints, and how to write constraints in the standard form for quadratic programming is something that this paper then talks about. Okay, and then they applied this particular example to paper machine control. This is the exact same paper machine control that I discussed with you in the previous week. Okay, in previous week the plant was non-linear, but the controller was linear MPC. In this particular paper they used a non-linear plant, and the controller was a non-linear model based sequentially linearized MPC. Okay, so that brings me, I believe, to the final example, and that is multirate estimation with measurement delays. And I will go over this very quickly because this measurement delay example I have taken at length in the other video, and I'm just sharing with you the paper that we had published almost 10 years back in Journal of Process Control. Okay, and the idea over there is you have a very tall distillation column, and what is measured in the distillation column, very similar to your assignment of week 9 and 10. What is measured is temperatures, but what you want to control is really the concentrations. Okay, but concentrations might still be available once every hour. Temperatures are available once every minute, concentrations are available once every 15 minutes, for example. Okay, but once you take a sample, it then goes through a gas chromatography system, and gas chromatograph takes anything between 5 to 15 minutes in order to give the results. Okay, so I might have taken the sample right now. Let's say at 4 p.m. I have taken a sample from when the measurement I get back from the gas chromatograph. It is not 4 p.m. but it's 4:10. Okay, so the measurement that I got at 4:10 doesn't pertain to the concentration at 4:10, but it pertains to the concentration at 4 p.m. So you need to quote unquote go back in time, implement that particular measurement at 4 p.m. and then compute the entire prediction from 4 p.m. to 4:10 p.m. Okay. Again, the trick now over here is you can do this much more efficiently rather than going back and recomputing everything, and you know that MPC is computationally heavy algorithm, so you don't need to do that. You can do that quite judiciously using state augmentation. Okay, so as I said, this is 4 p.m. okay, and the measurement has arrived at 4:10 p.m. okay, and between 4 p.m. and 4:10 p.m. we might have had 10 or 20 temperature measurements. So with these 10 or 20 temperature measurements, we kept estimating our concentrations and we kept moving on. When the concentration measurement arrived at 4:10 p.m. we were then directly able to correct the concentration measurement at 4:10 p.m. because this was a direct measurement of the concentration. Because of that, your accuracy of your estimator improves quite significantly. So it's quite important to implement these multi-rate estimation with measurement delays. Okay, and again, how to do that is to use state augmentation. This is exactly similar to what we had talked about. You have also done an example, and maybe there would be an exam question also, is if you have your GP equal to say k divided by tau s plus 1 e to the power minus theta s. Okay, how do you incorporate time delay in creating discrete state space model? Okay, you have already done an example in I think assignment 3 or 4. You know how to do that, and if you remember, we had stacked up pass delay models, UK minus 1, UK minus 2. Those were input delays. Here these are output delays, equivalent, not the same, because your input delay is like you have a pipe, input comes in at this end of the pipe and it takes 25 seconds for that input to come into your reactor. So you have a 25-second time delay, okay, which would be 25 divided by 60 would be your theta if your measurement time is 1 time unit, right? So that is what you have when you have an input delay. Here it is a measurement delay. That means the output is the one that needs to be augmented. So in the input delay we had xk, uk minus 1, uk minus 2. In output delay you have xk, yk minus 1, yk minus 2, and so on. Okay, that's the difference, but again the concept is exactly the same. Okay, the other way, we have then used a couple of other augmentation based methods which are more efficient, and you can look up the paper if you're interested in this. If you're interested more from completion of this course viewpoint or understanding of MPC, case 1 itself is sufficient, and we took multiple other cases also which are there in literature and demonstrated in that particular paper how various methods compare with each other, and these are the results for those comparisons. Okay, so I think that should probably be my last slide. Yeah, so the summary is we have discussed several practically relevant examples, 4 specifically. This is basically the summary of some of the important classical MPC papers that were published between say 1990 to 2005. So it is 15-year-old research, but these are quite important papers, and they do tackle problems of both practical, industrial as well as research interests. So thanks for listening, and I'll stop the video here. Thanks and bye.